Good morning, everyone. I'm Qinghang Wang from the high school affiliated to Renmin University of China. Today, I'm delighted to present my research titled Dual Prompt Learning for Readability Assessment of Ultra-Long Texts. Readability assessment plays a crucial role in education and content recommendation, but assessing ultra-long texts like entire books has long been a challenge. Our research aims to fill this gap with a novel dual prompt mechanism and a two-stage learning paradigm. Let's begin our exploration of this work. To keep our discussion structured, today's presentation will walk through 4 key parts. We'll start with an introduction to the background and challenges of readability assessment, then dive into the core of our model, the dual prompt representation module. Next, explore our two-stage learning paradigm, which addresses the length limits of pre-trained language models. And finally, present the experimental results that validate our approach. First, let's talk about the background of readability assessment. Readability assessment, often called RA for short, is the task of evaluating how difficult a given text is to read and determining which cognitive level of readers it is suitable for. Its applications are widespread. For example, in K-12 education, it helps create tailored reading lists for students of different grades. Over the years, RA has evolved from rule-based methods to machine learning approaches, but existing research still has 2 major drawbacks. The first drawback is short text bias. Most current studies only focus on processing short passage-level texts, like paragraphs or short articles. They can't handle ultra-long texts, such as entire books. Yet books are among the most common reading materials, especially for children. The second drawback is over-reliance on fine-tuning. Previous studies mainly used the fine-tuning paradigm to apply pre-trained language models, or PLMs, to RA. While PLMs have strong representational power, fine-tuning often struggles with long sequences because of PLM's fixed length limits, and it may not fully make use of task-specific information. These 2 issues are what drove our research. We need a method that can handle ultra-long texts and extract more targeted features for readability assessment. To address these challenges, our research makes 3 key contributions. First, we propose a 2-stage training paradigm. We transform the traditional token-to-book training process into 2 steps: token-to-segment and segment-to-book. This design directly eases the length limit of pre-trained models by first splitting ultra-long text into manageable segments and then integrating the features of these segments into a book-level representation. We can effectively process entire books. Second, we design a novel dual prompt mechanism to better capture representations of text difficulty. Third, our proposed model, named TTDP, short for two-stage dual prompt, achieves strong performance in ultra-long text RA. It outperforms traditional neural network classifiers like SVM and TextCNN, which proves the effectiveness of our design. Now, let's take a closer look at the first core component, the dual prompt representation. The dual prompt representation module, or DPRM for short, is the heart of our model. Its goal is to generate accurate text representations by combining 2 key inputs, the dual prompt and the text embedding. Let's break down the dual prompt mechanism into 3 specific steps. The first step is designing difficulty prompts. We define a set of difficulty prompt vectors, and these vectors are learnable parameters. During training, the model adjusts them to capture the most relevant difficulty patterns for RA. The second step is extracting linguistic prompts. To get text-specific linguistic features, we use the ZHVEAT toolkit, a tool specialized in extracting Chinese text features. We then pass these features through 3 separate linear layers to transform them into linguistic prompt vectors. This step ensures that raw linguistic data is converted into a format that works with the difficulty prompts. The third step is integrating the two types of prompts. Finally, we combine the difficulty prompt vectors and linguistic prompt vectors to form the complete prompt vector. With a dual prompt design, let's see how we generate the final text representation through 3 steps: embedding, encoding, and weighting. The first step is embedding. The embedding module accepts 2 types of input: raw text tokens and pre-computed token embeddings. No matter which type of input we use, the module processes it to produce the final embedding. The second step is encoding. We first combine the dual prompt vector and the embedding, then feed this combined input into the encoder of a pre-trained language model, such as BERT. The encoder outputs a set of hidden states, and this step fuses all information into a unified encoded representation. The third step is creating the final representation. To get this final representation, we weight 2 key components. One is the difficulty-related representation, which is calculated by averaging a specific set of hidden states from the encoder. The other is the linguistic-related representation, which is calculated by averaging another set of hidden states from the encoder. We use a learnable weight parameter to balance these 2 components when creating the final representation. Now, let's move on to the second core component, the 2-stage learning paradigm. This design solves the biggest challenge in ultra-long text RA, the length limit of pre-trained models. For example, BERT can only handle 512 quotients by default, while a single book may have more than 100,000 tokens. Our solution is to split the token-to-book process into 2 sequential stages: token to segment and segment to book. To visualize this, imagine a book being split into segments, each segment being encoded individually, and then the representations of these segments being combined into a single book-level feature. Let's break down the 2-stage learning into 4 practical steps. The first step is constructing segment data. For each book in our dataset, we split it into segments with a length that fits within the PLM's capacity. This ensures every segment can be processed by the PLM without exceeding its length limit. The second step is learning segment representations. For each segment, we input 2 components into the DPRM module: the dual prompt, which includes both difficulty and linguistic prompts, tailored to that specific segment, and the segment's embedding, generated from the segment's tokens. The DPRM processes these inputs and outputs a representation for the segment. The third step is learning long text representations. We collect all the segment representations of a book into a sequence of segment representations, then feed this sequence into the DPRM module again. The fourth step is difficulty level classification. To predict the book's readability level, we feed the book level representation, output from the previous step, into a classification linear layer. This layer outputs the probability that the book belongs to each difficulty category. During training, we use cross-entropy loss to optimize the model. To validate our model, we constructed a new dataset for Chinese ultra-long text RA. We named it Graded Children's Books, or GCB for short. Here's why and how we built it. There was a lack of large-scale datasets focused on Chinese ultra-long text RA, especially for children's books, so we needed to create one to test our model. We collected 320 Chinese books, including popular children's stories and classic novels suitable for young readers. In total, GCB contains 18 million characters, making it a large-scale dataset for ultra-long text RA. To ensure the accuracy of difficulty labels, we reference two authoritative sources. The first is Reading Guidance for School Students, issued by China's Ministry of Education. The second is the Basic Bibliography of the Library of Aiyue Primary School, a trusted list of graded children's books. Each book was assigned a difficulty level from 1 to 3, where Level 1 stands for low difficulty, Level 2 for medium, and Level 3 for high difficulty, all tailored to children's reading abilities. To evaluate our TTDP model, we compared it with three baseline models widely used in RA. The first baseline is SVML, an SVM model with handcrafted linguistic features, which represents a traditional rule-based plus machine learning approach. The second is standard SVM, an SVM model with text embeddings but no linguistic features. The third is TextCNN, a neural network model commonly used for text classification. We used 4 standard evaluation metrics: precision, which measures the proportion of predicted positive cases that are actually positive; recall, which measures the proportion of actual positive cases that are correctly predicted; F1 score, the harmonic meaning of precision and recall, a key metric for imbalanced data; and accuracy, the overall proportion of correct predictions. Our results show that TTDP not only handles ultra-long text effectively, but also outperforms all baseline models, even those that can process text of any length. For example, traditional SVM models, though not limited by text length, fall short in both accuracy and F1 score compared to TTDP, while TextCNN struggles more with long sequences due to its structural constraints. Why does TTDP perform so well? There are 2 main reasons. First, the dual prompt mechanism makes comprehensive use of difficulty and linguistic information, capturing subtle text features that baselines miss. Second, the 2-stage paradigm allows the PLM's strong representational power to be fully utilized, even for ultra-long texts. To make our results more concrete, we conducted a case study with 6 representative books from the GCB dataset. We compared TTDP's predictions with 3 other models: standard SVM, ERT fine-tuning, a common pre-trained model fine-tuning approach, and BERT p-tuning, a prompt-based baseline. Overall, TTDP correctly predicted difficulty levels of 4 out of the 6 books, outperforming all other models. The 2 incorrect predictions for books titled Animal Escape and Big Forest and Little Forest were due to subtle shifts in difficulty across different segments of the books. This is an issue we plan to address in future work. This case study further confirms TTDP's practical value for real-world ultra-long text RA. To wrap up, let's briefly recap. We proposed a dual prompt representation module to capture comprehensive text features and a 2-stage learning paradigm to handle ultra-long texts. Our TTDP model outperforms traditional baselines on the GCB dataset, proving its effectiveness for the readability assessment of long text like books. Now, I'm happy to take your questions.